give you a small introduction about myself. Excuse me. Hello? Perfect? Okay, focus. Okay, so first of all, I'm from France and I grew up exactly in Paris. This is my home city. All the little blue star is the place where I grew up. So Gare du Nord is where the street where I was. Then I had my elementary school, my middle school, my high school, and right here it was a university. So I moved out to Paris in 2005, where I did my PhD at the University of Fribourg in Switzerland. And during that time, I worked and I was introduced to the fabulous world of mycorrhizal. I worked on mycorrhizal establishment and understand the nutrition and the genetic regulation of mycorrhizal establishment in Virginia. And at the end of my PhD, I moved to the US in 2009, where I did a couple of postdocs. First, I was in New York, in fact, in Cornell, at the Wooster Institute, where I still work on epithelial mycorrhizal. And then I moved in Minnesota, where I worked a little bit on solving pathogen, soil nutrification, and turfgrass science. And that's why I applied for the turfgrass position in 2022. But in 2023, in August, I finally started my new position as an assistant professor at Ohio State, where I work on root, rhizosphere, and resilience. So I'm going to talk really go a little bit about the origin of mycorrhizal. And because really, during my PhD, I had to do a literature review on the origin, what are mycorrhizal, where are they coming from? And basically, this is this paper that made me fall in love with mycorrhizal. Because basically, they were able to visualize fossil structures of mycorrhizal that are like 400 million years old. And to showcase them to you, basically this is agricultural plant. This is like the cortex of the plant. And here you can see the output structure already completely done in this fossil. So I was very excited because I was working with a living fossil. So, moreover, and there was this other paper that shows that spore, the origin that was the first structures were found only 460 million years ago. So if you try to, it's a big numbers, but if you try to understand how here this is a fungal spore, there's a fossil fungal spore, and here this is a present-day spore. And so if you try to understand, okay, yes, it's like, no, but what does that mean in geological scale? Well, you see, this is what the spore was found in the sediment. Is the oldest fossil structure was cardiovascular mycorrhizal. Well, you can see that really goes with the origin of land plant. So this is a way, at that time, the continents were put together. So basically, the main hypothesis that I found remarkable was that the mycorrhizal may have helped terrestrial plants colonize the land. And so remember, I was showing you the fossil of Ohio Major. This is a schematic representation of Ohio Major, and you can see that this plant had no root system. There was this little structure here, and they were more to anchor the plant to the soil. So basically, mycorrhizal fungi, when they establish inside the roots, so here it's like really like carrot roots in the clay. They are going to form this very large, dense mycelium network that's going to go out of the roots and really forage into the soil. So basically, the idea was mycorrhizal was here to provide nutrient, phosphate, nitrogen, potassium, and water to these natural elements. So, most importantly, also another aspect of the mycorrhizal is it's so old that it also predates the diversification of plants. So basically, like the region you have like not a lot of diversity here's the beginning of mycorrhizal spore, observed here. Then you have all the diversification of plant lineage. It was during the time that you had this very large continent called Gondwana. So basically, it helped the avuscular mycorrhizal association. It could explain why the avuscular mycorrhizal association can be observed with most terrestrial plants, because the establishment was done before the diversification of the plants, and why it can be found in most continents. So every continent will have avuscular mycorrhizal present in their soil. So really, summary of this topic was that it's a science by somebody. We are working with a living fossil. They also have helped the colonization of land by early plants, and they predate the diversification of plant lineage. And so that's why we will see mycorrhizal association with most of the terrestrial plants. Now, whatever you have 4 different types of mycorrhiza: the mycorrhizal fungi, the ectomycorrhizal fungi, ecto-endomycorrhizal fungi, so 5 ericoid mycorrhiza that form with the species, and the orchid mycorrhiza. And for me, I'm very familiar with the avuscular mycorrhizal fungi. I would love to work more on the ectomycorrhizal fungi because they form this association and led to that truffle and changeable that I really like. So now, how do they develop inside the root system? So, as I mentioned, the spore is the first structure that is present into the soil. They are going to germinate into the soil. But the plant is going to showcase its presence by secreting, producing some compound, here is trigolactin, that's going to indicate its presence. And as a result, the spore is going to germinate and branch toward the direction of the plant, but also produce another type of effector that are going to tell to the plant, hey, I'm here, I'm coming towards you, and the plant is going to adapt to the fungus. So what's going to happen? You have this structure called aplasorium or lymphobium. Then you have the penetration inside the inner cortex and the formation of arbuscular structure. So this is a schematic representation, but I wanted to actually show you staining and microscopic picture, because it's very difficult to see the fungus inside the roots. So what you have to do first when you harvest your roots is doing the clearing with KOH, cleaning the roots, and then you can stain it with some stain that's going to attach to the fungal cell wall, and then you can actually visualize the fungal structure outside and inside the roots. So here there's the aplasorium. They can form coils. You have arbuscules here, what we call there an infection unit. Some mycorrhiza form a vesicule. This is a storage place inside the roots. And then at the end you have the spore. So what I want to mention is that mycorrhiza are obligate biotroph, meaning that they need a host to have a complete life cycle. Without a host, you will have the spore germinate and then go back inside the spore. Okay? Now, I wanted really to go a little bit further in the arbuscule. Arbuscule is a site of nutrient exchange between the plant and the fungus. So the fungus with this mycelium is going to forage into the soil and provide water and nutrient toward the plant. And this exchange is going to occur here inside the cell. And it's a symbiosis. And so it means that you have an exchange between those partners. So as a result, the plant is going to give sugar from its photosynthesis and lipid to the fungus. Okay, so that's why it's obligate biotroph, because there needs the sugar from the plant to develop. But if you think about this arbuscule, the arbuscule structure never destroys the cell. They never destroy the cytoplasm. It's not a pathogen. You have this membrane that will form, around the arbuscule, and the arbuscule lifespan is between 7 to 10 days, and at the end the arbuscule will degrade, and the cell can be reinfected. So here again is a schematic representation of how the arbuscule develops. You have the IV, a little trunk, resistance index. So, why is it important? This is the harmful, again, site of the nutrient exchange between the plant and the fungus. And so phosphate levels are going to inhibit colonization, but not only the colonization, also the presence of harmful. So during my PhD, that was one of the first graph I made, actually. I looked at like colonization of like an arbuscular mycorrhizal fungi in function of the gradient of phosphate. And you can see, so in terms of colonization, I'm looking at all fungal structure, internal life, and arbuscule. I can see it was decreasing higher concentration of phosphate. Now, when you look at the normal colonization, this is the abnormal colonization at high phosphate level. So not only you are losing your internal structure, like your internal hyphae, you are also losing the arbuscule. So there is no exchange now between the plant and the fungus. So, sorry, I moved too fast. Yes, okay. So why are we using arbuscular mycorrhizal fungi beside the nutrient uptake and the biomass? Well, this is because in the literature, in greenhouse experiments, in both chamber experiments in the field, there is an incredible number of benefits that are provided by their association. And we have resistance to drugs, resistance to salt stresses, better tolerance to cold and heat stresses, and also plant priming. So basically, the plant, by the presence of mycorrhiza, is going to be primed, and it's going to be more resistant to certain pathogens, not all of them. Now, is it true? So the main issues, this is, as I mentioned, all plants can be colonized by plant. 80% of the territorial plant can be colonized, but doesn't seem to have what we call a host specificity, but there is a certain what we call host specialization. So not all interactions are going to give you a positive result. And so this paper really showed, so this is that 64 different types of species that was tested with one fungus, one mycorrhizal fungus called Florence Sessoms. And here this is the percentage of change of biomass from the control. Mycorrhizal plant related to the control. And you can see that here you have an increase of biomass, where here you have a decrease of biomass. And it's very interesting because it's not really a pathogen, but it will lead to a decrease of the plant fitness here. Okay? And again, this is because of this nutrient exchange. The plant, there is a cost as being the cost to being colonized by the mycorrhizal fungi. So in addition to that, and I really did this from like this paper, not only the plant genotype or the fungal partner, the partnership between the plant and fungus can vary in function of each species. The presence of biotic factors, like for example, other bacteria, other like bacteria inside the soil, and also abiotic factors such as soil texture, like soil nutrients, presence of organic matter, can have an effect, an overall effect on the outcome of the association. And for us, what would be an increase in biomass, a better yield, maybe some quality, like testing quality, etc. of the fruit. So, in summary of that what I just said, this is arbuscule as a site of nutrient exchange. Phosphate will have a huge impact on the total colonization and the arbuscule presence. The arbuscular mycorrhizal symbiosis provide many benefits that are beside the plant nutrition, but the outcome of the interaction will depend on like the host and the fungus, but also on like environmental and microbial other microbial factors. So now, when I was asked to talk today, I really tried to do a little review on mycorrhizal present in pawpaw tree. You know, I was not very familiar with this tree and with the interaction between mycorrhiza and pawpaw. So I tried to look and do like really Google using Google and interaction. I could not find it with Pawpaws, so I went and I looked at the family where I come from, the Anaceae family, and after, again, by doing some digging, I found this paper that have looked online at all the different trees and different terrestrial plants and confirmed that there was that mycorrhizal presence inside this plant. And this is one of the tables, and in this table you can see that several Anaceae species were in fact colonized with arbuscular mycorrhizal family, so that's very interesting. So actually look at the reference and try to find the paper, and this is a paper with the custard apple, and you can see that there is actually fungal structure in it, so this is from their paper with a little arbuscule in it. But also when they were inoculating the custard apple, this is a control, and this is with inoculated plant, you have an increase of the increasing the height of the shoot and also the number of feet. So that was great. Then I looked at another reference, and I could see both of these species and the species are actually arbuscular mycorrhizal family. But what was interesting from these two papers is that, and again, we are thinking of management practice, it seems that the Anaceae family can only be colonized, as we know right now, with arbuscular mycorrhizal family, and not the ectomycorrhizal family. So if you are looking for, I would say, for an inoculum, I will focus on an inoculum that have arbuscular mycorrhizal family. Now, when I was looking at the summary of my detailed review, I was yesterday, and it's really yesterday at 11 p.m. I was like, okay, I didn't find any picture of mycorrhizal establishment in Pawpaw tree. And then it happened. So basically, I found from Florence State University. It's really a slide from a lab or a class. And basically here, there was what I call my uniform, the fungal structure inside the cell of the Pawpaw tree. So with a little arbuscule, the internal life. So here, this is the only time that I've seen fungal structures that are staying inside the Pawpaw tree. And it's really from a lab. A lab book for class taught at Florence State University. So, despite that, I did find microscopic picture. Pawpaw seems to be able to be colonized with mycorrhizal fungi. Anyway, the Anaceae family species can be colonized. There is fungal structure inside the roots, but more importantly, only arbuscular mycorrhizal fungi were shown to be associated with the species. So now, I've been told that most of you are using inoculum, like a mycorrhizal inoculum when you are transplanting your plant, because it helps with the plant establishment in the soil. And so, I was thinking, okay, that's great. If you think about the short-term practice, you want some fungal presence inside the soil to make sure that the plant is going to establish and